before we get started, here's a question for you. How many of you considered or looked at school rankings when you were applying to college? Yeah. Okay, how many of you didn't look at it at all? Yeah, a few of you, eh? Okay. So you probably looked at U.S. News and World Report, right? That's the biggie. Do you know what goes into the ratings? Anybody have the slightest idea what goes into rankings for school? Yeah. Wait, I'm sorry, what? Yeah, there's all sorts of factors that go in. But here's something that you may not have thought of. You know what constitutes the largest factor, 25%? Ratings by other colleges, right? Because that's what they do. U.S. News and World Report sends out surveys to the various colleges, and they rank each other. That's 25% of the rankings. Isn't that fascinating, right? Is that what you would choose? You know, if you're head of a college, how am I going to rate Harvard? You know, it's an interesting factor that they're counting so much. Another thing that's a big factor, less than that, but still part of it, is the admissions rate. The admissions rate, right? If they can show that they're a selective college, that they don't take in as many people as have applied, then it increases their rankings. So what some colleges were doing were sending out what they called FAST apps or SNAP apps, which are applications essentially by email and other things that fill them in. They fill them in for you, essentially. All the information except for a couple other things that you have to fill in for 5 minutes and send them back, encouraging a big application rate. They're still not taking in a lot of people. All right? So what happens is more people apply, but they're still not taking in a lot, which boosts their ratings because they look like they're being very selective. Another thing that goes in is the proportion of alumni who donate to the university. So there was this one anecdote of somebody being sent $5 from their university with the request that they turn around and send it back. Because if they send it back, then that could be counted as a donation. So it's very interesting, right? Yeah, you're like, oh, I didn't know that. You know, when people give rankings and things like that to you, you should really ask what went into it. I mean, SAT scores. And we've been talking about outliers and things like that. Well, you know, SAT scores, average SAT score goes into the ranking as well. What's to keep a university from saying, you know, these students who aren't doing so well, maybe we'll call them probationary students. And since they're probationary, we won't put them into the mix. So you cut out the lower SAT scores, and you've raised your SAT scores. Okay? There were rumors that Sarah Lawrence College was going to be in trouble because they stopped collecting SAT scores. And U.S. News and World Report were rumored to be putting in the lowest possible number for them, which would have affected their rankings. I don't know whether that happened or not. But like I said, it's just really interesting when somebody gives you a ranking of something, you want to ask what factors went into that ranking. Because it may surprise you. It totally surprised me to realize that rankings by other schools counted for 25%. That's a big amount. Okay? So anyway, that was just, this is stuff that amuses me. I know, you have better things to do with your time. But. Okay, let's get back to what we were talking about last week. And the big topic that we were handling that you really need to get on top of is the idea of a sampling distribution. A sampling distribution. Now, for gold star, does anybody remember what a sampling distribution is? What is a sampling distribution? It's really key to understanding what it is we're trying to do. Remember, first we started off with finding z-scores, right? Finding z-scores for individual scores. Right? What did z-scores tell us, by the way? Before we get to a sampling distribution, what did the z-scores tell us? Just good old straight z-scores. Yeah. Right, it told us how many standard deviations above or below the mean. What did that turn into that was even more useful than distance from the mean? Yeah. Yeah, percentile ranks or probability, right? We got probabilities, proportion, percentages, percentile ranks from that, yeah? Okay, but we need to be able to find probabilities for what? Not just individual scores, but what were we looking for probabilities of? Not ranges per se. Yeah, means, right? We want to know the probabilities of means because when we do experiments, we get groups and then we have means and we want to know the likelihood of those results. And that's why we started talking about a sampling distribution, right? In particular, the sampling distribution that we talked about was the sampling distribution of the means. The sampling distribution of the means. So what is it a distribution of? It's a distribution of means. Any old means? No, means of a particular sample size. Every time you take a different sample size, you could be creating a different distribution, right? Like the example we did was a population of 4 scores, and we took a sample of size 2 from that population, and we created a sampling distribution. That was one sampling distribution when the sample size was 2. I could have created another sampling distribution from that population with a sample size of 3 or 4, right? Those would be different distributions based on the sample size, okay? What's the mean of a sampling distribution? What is it equal to? The mean of a sampling distribution of the means, yeah. No, it's not 0. Actually, we will come to a different sampling distribution where that's the case, but the sampling distribution of the means, what is it equal to? Yeah? The population mean, right? And what was the standard deviation of the sampling distribution? What was it called? It wasn't called the standard deviation. Yeah. Standard error. And it was related to the standard deviation by what? The standard error is related to the standard deviation of the population by what? Yeah. Sample size. Yeah, n, right? Right? It's the standard deviation divided by the square root of n. As your sample size gets bigger, what happens to your standard error? It gets smaller. It gets smaller, which means that the distribution of those means is getting narrower and narrower, which means essentially it's honing in on a better estimate of your population mean, right? It's getting more and more precise. That's exactly what's going on. Okay? So that's the sampling distribution of the means. So we use that to find the probability, the likelihood of getting a particular mean. Okay? So we're going to start off this morning doing examples like that because we did. I want to make this distinction because usually I do both things in the same class and then it's real clear when I'm going from individuals to means. This time we had already done individuals, now we're doing means, and you just want to make sure that you understand the difference. Okay? So now we're going to be finding probabilities of means. So let's take a look at the kind of questions that we ask and what we're going to be doing. Okay? Well, first of all, let's just put this up. Okay? We're going to find a z-score. It is going to be a z-score to help us determine the probabilities of means. Actually, we can do. Let's move this down. Okay? But look at the change in the formula. Right? The change in the formula is just how far is my sample mean from my population mean? Because that's what I really want to know. How far is my sample mean from my population mean divided by the standard error? Right? That's a standard error. So what you're going to do is essentially find out how far is your sample mean from your population mean in standard error units. In standard error units. A z-score tells you about how far a score is away from the mean in standard deviation units. And this tells you how far your sample mean is from your population mean in standard error units. Okay, so let's do an example. Here we go. Suppose we know that the average weight of 6th grade boys is normally distributed with a mean of 99 pounds and a standard deviation of 4 pounds. What's the probability of obtaining a sample mean of less than 98 pounds? Okay, so this is very similar to the kinds of examples that we've done, but now we're asking questions about means. Okay? First of all, why would I be interested in this question? Why would somebody be interested in this question? What's the point? Why do I care? Weight, 99 pounds, 98 pounds, yeah. Yeah, okay, right? I'm interested, especially these days. Now I guess we're more concerned with obesity rather than underweight. But yeah, to find out how likely, but not how likely an individual is, but how likely it is to get a mean from a group of 25 boys of 98 pounds or less. Is that a typical occurrence? Is that an unusual occurrence? We don't know. So let's draw a curve. Okay. What's the mean of our distribution here? What's the mean of our distribution? 99 pounds. Okay. And the mean that we're interested in? Yeah, 98 pounds. So what's the area that I'm looking for? In this question, what area am I looking for? Yeah, it's the area beyond. It's below here. Right? Now, the difference between 98 and 99 pounds, it's only 1 pound. So you might think like, well, who cares? That's not going to be a big deal. But let's see what this turns into. So the first thing we have to do is we have to transform this into a z-score. Now, if you remember before, what I had was these were x-scores. And the truth is, it's still the variable x. It's still weights in this case. But you can also think of it as means, as possible means, if that's useful. And then we're transforming it into z-scores. What's the mean of the z-score distribution? 0. Okay? And this is what we have to do. Okay? What am I missing? What am I missing here? Yeah, standard error. I don't have the standard error. So the standard error is equal to the standard deviation divided by the square root of n. So what was the standard deviation here? Yeah, it was 4 pounds. And n was 25. So my standard error is 0.8, 0.8 of a pound. Again, remember, a standard error is going to be smaller than a standard deviation. Depending on how big your sample size is, will determine how much smaller. Okay? Yeah. Sure. Let's see. Which way are we going to move it? Well, let's try. Is that better? Well, sort of better, right? Maybe there. Okay. All right. So let's plug it in. So what do we have? 98 pounds. We know it's going to be a negative z-score. 99 is our mean, divided by 0.8. So, right, that's minus 1.25 standard errors below the mean. 1.25 standard errors below the mean. Okay, now what? Now what do I do? Go back to the question. What was the question asking? The probability of obtaining a sample mean of less than 25 pounds. So what do I have to do? Yeah, I go to the table, and I look up a z-score of 1.25, right? The negative and the is just the flip side of the positive. Which column am I looking at for the area? Yeah, beyond z, beyond z. So if I do that, I get a probability of, what is it, 0.1056. Okay, so the question is, that we're not answering yet, but is that likely? Is that unlikely? What do you think? Is that a rare occurrence or a common occurrence? If you were just going to make a subjective evaluation of it, what do you think? 0.1056. 10 out of 100. Rare? Common? Oh, Lord, wake up, people. I know it's Monday morning, but like you're all looking at me like, yeah, it's Monday morning. Rare? Yeah, it's like it's one of those things that you might say is borderline. It's not very, very rare, but it's not real common either, right? And we're just talking about a difference of 1 pound. What would happen if I had taken a larger sample size? Follow the chain of events, okay? If I took a larger sample size, what would happen to my standard error? My standard error would get smaller, right? What would happen to the z-score? The z-score would get bigger. What would happen to the probability? It would get smaller. Follow that chain of events. You want me to repeat it? Because this is something that happens, and you have to know like what's affecting what. You know, like I said, very often a lot of the details are going to change, but I want you to understand the relationships here. As sample size increases, my standard error decreases. Yeah?
How did you get from the standard error to the probability?
Okay, wait, can you hang on to that for a second? Let me finish this chain of thought, okay? Right? As sample size increases, standard error decreases. As standard error decreases, your z-score increases. As your z-score increases, the probability decreases. Say it one more time. Okay. Standard error, as sample size increases, standard error decreases. As standard error decreases, z increases. Right? It gets more extreme. It gets more extreme. As z increases, or it gets more extreme, you could think of because it's on the negative side as well, the p-value, the probability decreases. So that you understand, sample size affects the probability of your result. Okay? Now, your question. Say your question again.
How did you get from the standard error to the probability? Or how did you get the probability?
Well, the probability is from a table.
Oh.
It's from the table. It's from the z table.
Oh.
Okay? We looked up a z-score of 1.25, and we found the probability in an area there. Yeah?
Is that the probability of finding someone under 98 pounds in the sample?
No.
In the population?
No. It is the probability of finding a mean of 98 pounds or less. Finding a mean, not an individual. The probability of finding an individual of 98 pounds or less is a whole different probability. That we would have calculated the way we did with regular z-scores. But this is the probability of finding a mean when you take a group of 25 boys of 98 pounds or less. Okay? Other questions? Right? The computations on this is all going to be really straightforward. I just want you to understand these concepts behind it. Okay? Let's do the other question here. Yeah? No, that's the likelihood of that particular mean in the overall population. In the overall population, yeah. Because that's what we have. We have the parameters on what the normal population is, that the boys are 99 pounds with a standard deviation of 4 pounds. Given that, if I came across a group of 25 boys who had a mean weight of 98 pounds, how likely is that? It's not as likely as you would think. Yeah?
So what, I mean, in general, is that an appropriate sample size, or what?
She said in general, is that an appropriate sample size? Sample size is a really good question. It really depends what you're doing. No. The 30 and 40 guidelines, and we'll actually get back to that again, but remember what that was for, okay? I said that a sampling distribution, there's two parts to the shape of a sampling distribution. And I might as well mention them here again anyway, right? Because we know the mean of a sampling distribution, we know the standard error of a sampling distribution, so then there's the shape, right? So what is the shape of a sampling distribution? Two things. If the underlying population distribution is normal, the sampling distribution will be normal as well, right? You're taking samples from a normal population. That's fine. What if your population distribution is not normal? Then your sampling distribution will be normal if the sample size is large enough. That is 30 to 40. Okay? In this example, what do we have? The population distribution is normally distributed. Okay, so it's going to be normal. But yeah, but sample size is actually an interesting question because it really varies depending on what you're doing. You know, the kind of common wisdom is that bigger is better, but you know, it doesn't always turn out that way. Okay? All right, so let's do this other question here. A soda company puts their bottling machinery to put a mean of 16.5 ounces of soda in each bottle with a standard deviation of ½ ounce. Soda is packaged in 6-packs. Assume that each of the bottles in a 6-pack is a random sample. What percentage of 6-packs have a mean bottle amount of 17 ounces or more? Okay? Now, why would you be interested in how much soda a bottling company puts into their bottles, either more or less? Why would you be interested in that? Who cares? I know this morning you don't, but who else would? Who else would care? Yeah. That's right. That's right. If they put more soda in than they want to be putting in, they're losing money. If they're putting in less soda than they should be putting in, that's fraud. Right? So this is quality control. You have to know that your bottling machinery is doing what it says it's going to be doing. So people, you know, companies will do that. They'll have to take samples and measure stuff to make sure that it's within a certain range of error so that you're not either losing money or defrauding customers. Okay? All right, so let's do this. So again, draw a picture. Like I said, you don't have to. I find it easier to understand what I'm doing, but you wouldn't be marked off for not drawing a picture. Okay, what's the mean of this distribution? Let's see. 16.5, right? And what's the mean that we're interested in? 17. Okay. What's the area I'm interested in? The probability. Where does it show up on this curve? Yeah. This area. Okay, 17 ounces or more. Okay. What's the thing I'm missing here? Yeah, standard error. Good. So my standard deviation is, it's only ½ ounce, okay? We're not talking about big numbers here. What's n? What's n? Yeah, 6. Okay? So we have 17 divided by 0.204. So we have a z-score of 2.45. Before I even look up the probability, is that going to be a large probability or a small probability? Oh, I'm hearing a lot of smalls. Oh, yeah, good, right? Because the z is very large, right? It's all the way out there. And we know that a z of 2 is already getting to have a small probability. Well, so what column do I look this up in? Yeah, beyond. So the probability for this is 0.0071. Okay? So understand something. Even though we're only talking about half an ounce, the likelihood of that happening is very, very tiny, less than 1% of the time. Okay? Which is what a company would want. They would want it to be a very, very small percentage of the time. That's if you take a mean of a 6-pack. Okay? Questions on this? This is all things about means. Yeah, did you have a question? No, questions. Okay? So we're going to be using this kind of format to answer other questions. Now, because we're getting into these probabilities, and in the next chapter we're going to be talking about actually testing things and making decisions using these probabilities, there are certain assumptions that go along with these procedures. Okay? So let's take a look at this assumption. The first assumption, the assumption is the variable follows a normal distribution in the population. Okay? Now, the central limit theorem saves us. All right? Remember, the central limit theorem, again, is saying basically, you can read it up there. I don't know how understandable it's going to be to you, but sometimes the wording gets a little confusing. But it's what we just said at the beginning of class. The mean of the distribution is going to be the population mean. The standard deviation is going to be the standard error. And the shape will be normal if the population distribution is normal, or normal if the population distribution is not normal, but your sample size is big enough. Yeah. I mean, it's like I said, it's up there, but do you want me to say it in small words? Yeah. Yeah, okay. Just the last part, the shape part, or all of it? All of it, okay. Okay. The mean of the sampling distribution of the means will be the population mean. The standard deviation of the sampling distribution of the means will be the standard error. And the shape of the sampling distribution of the means, and there's two parts to this, okay? One will be normal if your population distribution is normal. It'll be normal if your population distribution is normal. Or two, it will approach normal if your population distribution is not normal, if your sample size is big enough. Okay? Okay? So when we talk about that it's normal, this is like what we're relying on the central limit theorem, this production of normality, because there's a variety of different things that are not normally distributed. But the central limit theorem shows us how we get to normal, right, for the means, and then we can find our probabilities based on a normal distribution. All right, that's the benefit of it. Okay. The second thing, the samples are selected randomly. Okay. Now, there's actually two parts of this. This is sometimes called simple random sampling or independent random sampling. There's actually two parts to this. One is the random sample part. What does that mean? That means that every sample has an equal size, an equal chance of being selected. Every sample has an equal chance of being selected. The independent means each selection must be independent of the other selections. Right? Like if I choose somebody, I don't want to be choosing their sister as well, right? You don't want, independence within a statistics context means that selection of one thing does not influence the selection of another thing, that the probabilities are not intertwined in some way. So that's really what you want. So in theory, you're meeting these assumptions when you're doing these procedures. Okay, let's do a couple more examples. You don't have these, so I'll give you a minute to write them down. Okay. Another moment. Bless you. Okay, so let's look at the first question. Suppose that the ages at which children first walk alone are normally distributed with a mean of 11.5 months and a standard deviation of 1.1 months. What percentage of children first walk at age 12.3 months or older? How do we answer this question? What kind of question is this? How are we going to answer this? Well, what do I have to find? What am I looking for? I'm looking for Z, okay, because I'm looking for a percentage, really, right? I have to get to a percentage, so I need Z. Is this talking about individuals, or is it talking about means? Individuals, okay? So that's just a straight Z-score using the standard deviation. So what do we have here? What's the mean of this distribution? 11.5. And what's the score that I'm interested in? Yeah, 12.3. Okay. The area that I'm looking for? Yeah, 12.3 or larger. So that's this. So that's a simple Z-score. What was the standard deviation here? 1.1. 0.73. A Z-score of 0.73. By the way, it's useful to remember, just kind of in your head, that Z-scores plus and minus 1 cut off about how much of the distribution? Anybody know? About 68% of the distribution. So about 68% of the distribution falls between plus or minus 1. That should give you some indication of where things fall. Okay, so that's a Z-score of 0.73. We look that up in the table, and the percentage is, right, the probability is 0.2327. So the answer is the percentage of kids is 23.27%. Okay. Now look at the next question. Suppose the kindergarten classrooms are created by randomly selecting individuals from the children population. Each kindergarten class has 20 children in it. What percentage of such classrooms have a mean first walking age of 12.3 months or older? Okay, what kind of question is this? What am I looking for? Probability of what? Yeah, probability of means. The probability of a mean. Okay, so the mean of the distribution is still 11.5. The mean I'm interested in is 12.3. Okay, and I'm still interested in this area. All right, what do I need? Standard error, yeah? So the standard error is going to be 1.1 divided by what? The square root of what? 20, good. That's my standard error. So then my Z-score, right? Again, it's how far is the sample mean away from the population mean? How likely is that? Not very. Not very. If you were to look up the probability in the back, yeah? And again, what area am I looking for? Beyond, okay? There's a Z of 3.20. The probability equals 0.0007. But then it jumps to a Z of 3.40. Okay? In this procedure, for this chapter, I'm expecting you to go to the one that's closest. The one that's closest. That rule is going to change depending on what we're doing, but for this stuff, it's what's closest. So, what's the answer to the question? Yeah, 0.07%. 0.07%. You expect to get a mean of 12.3 or more from a sample of size 20. Again, I can't specify that enough because what if the sample was only 5? What if the sample was only 5? Would the probability be smaller or larger than what we found? If I change the sample size to an n of 5, would the probability be smaller or larger than what we found here? Larger. Larger, right? Because if I made that n smaller, this is just the reverse of what I was saying before. If n is smaller, my standard error is bigger. Bigger. So then z is smaller, and the probability will be larger. Okay, it's just the reverse of what I said before. Okay, questions on this? Questions on this? Yeah. Usually a standard error is some kind of intermediate, right? She was just asking about how many decimal places. Usually it's an intermediate calculation. If I asked for a separate question, what is the standard error? Then you could round it to 2. But if you're going to use it in the Z, you really should carry it to 4 decimal places. Yeah, intermediate steps really, truly should carry to 4 decimal places. You'll wind up with a lot of rounding errors if not. At the end, the last, when you're just giving the answer to the question, then you can round to 2, but otherwise really carry it to more. Okay? Okay, good. That's it for chapter 4. Now we're going to take this information and we're going to start being able to use it in a different way. Okay, this is kind of the overview of what we're going to be doing. We now know, we have some idea of how to get the probability of means. Now what I'd like to do is figure out a decision rule. How do I make a decision when somebody tells you this drug is better than that drug? Or going to Kaplan's increases your SAT scores. And they look at you and they say things like, we have found statistically that, yada, yada, yada. How do they make those decisions? That's what Chapter 5 is about. Taking the information that we have. And it's a procedure called null hypothesis testing. Null hypothesis testing. And like I said, essentially what you're doing is you're finding probabilities and developing a decision rule for when you say something is due to chance and when something is due to whatever effect it is you're looking at. Okay? Let's take a look at an example that we're going to walk through. Okay? Suppose we wish to know whether children who grow up in homes that are close to electric power stations have higher IQs than those of children whose homes are not close to power stations. In the general population, IQ is normally distributed with a mean of 100 and a standard deviation of 15 points. This is a given, folks, right? We've talked about IQ before. We take a random sample, n equals 25, of subjects who live near power stations and measure each subject's IQ. And I think on your handouts it says who have pets. I think there's a typo there. Yeah, somebody pointed it out to me the other day. It should be close to power stations. There's another version of this example. So some people have pets. Some people live near power stations. Okay. Now, one thing down here, these assumptions, an equal chance of being selected. Now, this is a difficult thing. This is a very, very difficult thing to meet. It kind of assumes that you know where all the power stations are located in the country, all the kids of a particular age are located in the country, and you can get their IQs, and then randomly select those children. Doesn't happen often. Okay? Just pointing out to you the problems, it kind of limits your generalizability, but understand that. And they're independent. If you choose one child and get their IQ, you don't want their sibling necessarily or their cousin. Okay? Now, what are you going to do with this? Well, first of all, so we get these kids, right, these 25 kids, and we find out that the mean of these kids is 103.48 in IQ. The question is this 103? It's not 100, right? So is that 103.48, is that due to chance? Or is it due to the fact that they live near power stations? That's our question. Okay? Understand something. Every time I take a sample of kids, a different sample, every single time, in general, I'll find a different mean. Right? I could even have, if you guys are my population and I take a sample of your test scores, I take a sample of 5 people and I get one mean. And then I take another 5 and I get a different mean. Right? I could keep doing that over and over and over again. I'll get all sorts of different means. The question is that just due to chance? Right? Well, in that kind of scenario, yeah, it's likely due to chance. But in this case, we're hypothesizing that living near power stations affects your IQ in some way. So our basic choices are going to be, is this due to chance or is it due to the power stations? And we know that the means will vary just by chance. So how do we make a decision? Okay? Null hypothesis testing is what we call an indirect way of proving your case. First of all, I have to make the comment, we don't really prove anything. We give credence to, we strengthen the evidence for, we lend support to, okay? I would be very loath to say, I have proven X, Y, Z. There's always room for error. There's probabilities we're talking about. There's room for error. But given that, null hypothesis testing is a way of indirectly doing this. Because what I can't do is I cannot prove that kids who live near power stations have exactly a mean of 103 or 105 or 110, right? Because there's an infinite number of possibilities that their mean could be that's not 100. I can't prove that. All I can prove, and we'll put that in quotes, all I can prove is that they're not 100. That's why it's indirect. I can't prove that they are this. I'm going to try to prove that they're not that. That's why it's indirect. Using the wording in his book, and because I just want to explain it so it's clear. What we're doing is, he says, take the worst case scenario and assume that it's true. Now, what he means in this context, like in this particular example, his idea of worst case scenario is that the mean of kids who live near power stations is exactly the same as the mean of the general population. That's his idea of worst case scenario. All right? That essentially these kids are not different. They're not different. They're not different from anybody else. All right? Try to show that this assumption leads to ridiculous consequences. If they're ridiculous, we can reject it. Okay? In this context, what he's saying is this. Let's imagine for the moment that the mean of these kids is not 103.48, okay? Because that's close. Let's imagine for a moment that the mean of these kids from power stations is 120. Okay? So he says, in null hypothesis testing, what we're doing is our assumption is that these kids are no different. That 120, yeah, it's really by chance. And really, they're no different from kids who have a mean of 100. But we take that 120 and we show that that's got to be ridiculous. How do we show that that's ridiculous? We find the likelihood of it happening. We find its probability. How probable is it to get a mean of 120 if the population mean is 100? How likely is that? You have some idea now. Would that be likely or not? Not very likely. If that is so unlikely, what happens is if it's very, very unlikely, we say, you know what? That can't be chance. It can't be chance. It must be due to something different about those kids. If the probability of it happening is so small, then we say, yeah, that's ridiculous. And we can reject it. And if we reject it, then we're left with the idea, yeah, these kids are different. Okay, so you understand what's going on. We say, no, they're the same. We get their mean, and we find out how likely that is. How likely is it that they're the same? Well, not very based on this data. So we say, okay, that can't be true, and we're left with the other idea that they're not the same. That's basically what's going on. I'll keep talking about it, but that's the basic idea. So in this case, what we're going to have to do is find out how likely is a mean of 103.48. Now, I talked about some of this. So let's just see if there's more stuff here. Right? What we're going to do is we're going to set up two hypotheses. And these hypotheses are possibilities about the state of the world. The one hypothesis that I've been talking about is called the null hypothesis. And generally, it's a statement. The null hypothesis is generally a statement of no difference. No difference. Okay? Now, and we'll talk about the second one in a bit, the other hypothesis in a minute. in order to find out the likelihood of my result, right, my mean of 103.48, I need to find a distribution that does that for me, right? That's what we've been talking about. How do I find the probability of a mean? Well, what do I go to? A sampling distribution of the means. In this case, in this very simple case, the null hypothesis distribution, that's what we're calling it, because it's a distribution based on the null hypothesis being true. A distribution based on the idea that the null hypothesis is true. So in this case, our null hypothesis distribution is simply the sampling distribution of the means. It's just where we're going to find our probability. And so we know that, okay? So the sampling distribution of the means gives us the probability of the means given that the null hypothesis is true. You have to make an assumption that the null hypothesis is true in order to generate a sampling distribution. You have to start from somewhere. The somewhere we start from is that the null is true. And based on that, we get a distribution. Okay? So we know this stuff. IQ is normally distributed. Normal distribution, we have all that. We know we need the standard error. And now we're going to find the probability. All this we've done so far. We've just been talking differently about the concepts behind it. Let's actually do that for this example. What I'd like to find out is the probability of getting a mean of 103.48 or higher. That's really what I'm looking at. So we know this. IQ, mean of 100. Kids, 103.48. I'm looking for this probability. What do I need to find this? What steps? What's the next step here? It's not a rhetorical question. Yeah, standard error, right? I'm going to find a z-score, so I need the standard error. What is my standard deviation? It's 15. And what's n? Yeah, it's the first page. Yeah, 25. So my standard error is 3. So my z-score right, because the difference between 103.48 and 100 is not all that big. But we won't know until we take into account our standard deviation and our sample size. So we have a z of 1.16. Okay. Have to find the probability. You know how to do that already, right? Beyond z in that column. The probability of it happening is 0.1230. That's this area. So the question is, okay, the probability is 0.1230. What can I make a decision based on this? Well, first of all, I need to give you more words, more terms. This probability is called a p-level. A p-level. P-level. And is the probability of your result given the null hypothesis to be true. Okay? It's the probability of your result. Yeah. P-level, yeah. P-level. Okay? So look what we're going to do, right? We transform it. What we have to do is set up, actually, let's put this back. I want to do it this way. I have to set up some kind of criterion for what I consider rare and what I consider common. Okay? Because what this is saying is, okay, the probability of getting a mean of 103.48 is 0.12, or higher, is 0.1230. right? By chance, just by getting it by chance, that's its probability. If I say that getting a mean of 103.48 is because they live near power stations, I could be making a mistake, right, with that probability, because just by chance that could happen. So how big an error, how big a mistake am I willing to make? Well, the convention that's come down in the behavioral sciences anyway is a probability of 0.05 or 0.01. This is called alpha. Alpha. Alpha is essentially the risk you're willing to take. And it's a criterion for what probability you set for this decision. What constitutes rare or unlikely, and what constitutes likely or common. So what we're going to be doing is saying, if I get a result whose probability is smaller than alpha, whose p-level is smaller than alpha, then I'm going to say, that couldn't be due to chance. It must be due to something different about those kids, that drug, whatever. Do you understand? What I'm saying is the probability of it happening is so small that I've decided it must not be chance. But what's the kicker? It could still be chance. It could be still chance. This is what I want you to understand, all right? These decisions that we make, there's an arbitrary quality to it, right? It's come down traditionally that our alpha is either 0.05 or 0.01. 0.01 is a stricter criterion. But it could have been 0.06. It could have been 0.07. It could have been 0.03, right? It's just come down conventionally that this is what we do. And there's still a small chance that we're making a mistake. Okay? This is kind of, you have to understand that. So if the probability of our result, if our p-level is smaller than alpha, we reject the null hypothesis as a possibility. If our p-level is smaller than alpha, right? I'm comparing two probabilities there. If our p-level is smaller than alpha, I reject the null hypothesis as a possibility. When I do that, I'm saying that my results are statistically significant. That's a particular phrase. If somebody says that their results are significant, that means they've gone through this process. Okay? Yeah. Yeah. If your p-level is smaller than alpha, you reject the null hypothesis. We say that our results are statistically significant. Okay? It's like I said, it's a particular term. It's a stats term that you'll see. If somebody claims that their results are significant, it means they went through this procedure and determined that the probability of their results were so small that they were saying that it couldn't have been due to chance. Okay? This is the basic, these chapters, this 4 and 5 are like the basis of the entire semester. Getting to the idea, the concept behind hypothesis testing. The rest of it is all going to be detail. So it's really important that you get that. Let's take a look at this example for a minute. What do we have here? Let's say my alpha is 0.05. I'm willing to take a risk of making a mistake 5 times out of 100. Okay, or 1 time out of 20 if you want to look at it that way. Are these kids different? Are kids who live near power stations, does that mean significantly different from the rest of the population? No, right? Because my 0.05 would be, let's say, here. Okay? The probability of that happening, of 103.48, is bigger than that. So we say, no, that difference in mean must be due to chance. What we say is that we fail to reject the null hypothesis. We fail to reject it. By the way, people are funny about it. Very often, we don't say we accept the null, and that's just kind of come down traditionally, philosophically, because the statistician who developed this, Fisher, his name was, he didn't like the idea that we accepted the null, that what we were doing was not true. Rather, he said, we failed to reject it. Like, we haven't rejected it yet. We don't have sufficient evidence to reject it. But he was hanging on to the idea that maybe we could reject it. Because very often, you do want to reject this idea that something happened by chance. Right? When you're doing research, usually you're not looking to find results that say, oh yeah, this just happened by chance. Usually, you're manipulating something, you're observing differences in groups. So you don't usually want a result. You don't want the null to be true, sort of, yeah? If you're failing to reject the null, then what you're doing is you're hanging on to the possibility that your result could have been due to chance. Right? That 103.48, okay, it's greater than 100, but it could have just been due to chance. Right? It wasn't that they lived near power stations. That you're saying that it is true, quote unquote. I'm not sure I'm getting what you're saying. Try it again. It's a hypothesis that, in literal terms, it's a hypothesis that these kids are not different from the general population. Yeah. Another way, by the way, in terms, like I said, I'm throwing terms out there to you because you're going to hear them, right? One way of thinking about it is, another way of rephrasing the question is, are children who live near power stations, do they constitute a different population from the general population in the country? If they were different, we would say, oh, they must belong to a different population. That is, the population of kids who live near power stations. But since they didn't, we say, no, they must belong to the general population. It's just another way of phrasing it, so if you hear that, you shouldn't be thrown by it. Other questions on that? Let's take a look at some of these things and see if I've told you everything I need to tell you here.